We have started the recording. Okay, I think we will get started. To give you a quick recap, in this topic, we are discussing about various types of security issues associated with blockchain, where we talked about some of the common risks and some specific risks. And under the specific risks, we talked about the vulnerabilities and security issues that originate due to the blockchain basic operation mechanisms. And we said that for smart contract execution, of course, there are different other types of risks, just because that is again some piece of code running. And the usual types of vulnerabilities associated with any form of such running of codes are also there for smart contract execution. So out of the common risks, we have been talking so far about 51% vulnerability, then security of the private key, then a little bit of tangential topic about possible criminal activities that make use of the characteristics of blockchains, including ransomware, then underground markets, different deals, and also possible money laundering. We talked about double spending attack uh, in a typical scenario, and of course some of these attacks can be combined, and then they have more impact or higher impact. And then finally, in our last lecture, we talked about selfish mining attack, where we discussed about that if there is a mining pool which can generate these blocks, need not be at the same rate. It would be typically at a slower rate. But if they are very diligent and they keep noting the number of blocks they are able to mine vis-a-vis the number of blocks that have been added to the public chain. So depending on that, they could decide whether to publish their private chain, and thus go a step ahead of the actually publicly known branch. And we saw the different possibilities as to when this block can might get mined by the attackers group, or with respect to the blocks actually being made public. And depending on that, based on the situation, it can decide when to publish its blocks, and how many of those to publish, because it may want to accrue the revenue as it keeps going. And when especially it sees that the public chain is almost catching up with its chain, and which is likely to be more than that of the attackers pool. We looked at these 8 different situations, and we saw what would be the revenues that the attackers can actually accrue because of maintaining these chains, and deciding to publish it from time to time, depending on how well the public chain is progressing. So that is what we talked about in terms of selfish mining attack. So today we will talk about two more types of attacks. One is the so-called eclipse attack, and the other is the front-running attack. Now, these two also are available in the respective papers, which are there in the last slide. Now, if we see that the attacks that we talked about so far, these are something related to the basic protocol, the high level protocol of blockchain. They are not so much about the underlying network infrastructure, whether there could be some attack on that. So this particular attack, this Eclipse attack, that shows that the underlying the networking protocol, like how the peer-to-peer network is set up in these blockchain networks, how that can be actually compromised, or how vulnerabilities in that peer-to-peer network formation and maintenance, that protocol can be actually the vulnerabilities of those can be exploited. So that is what this Eclipse attack is all about. And of course that the goal would be to first carry out this attack, and then on top of it, of course, for actually profit making, some of the other attacks, as we mentioned, like double spending and all, that can be carried out. So let us understand the basic concept of Eclipse attack. So suppose there is a node in the network which is the target victim of the attackers. So normally, say when the this node, for example, joins the network, if you remember, we said that as it joins, it installs. Say let us assume all this in the context of Bitcoin, but it can hold for other networks also. Now, for these types of networks, what it does is that it gets the peers. So that is what we had studied, and gets the peer network from, and then from there it will be communicating. From then on, it will be communicating with the peers, who in turn will be communicating with their peers, and in this way, any transaction originating from this node will also reach the internet network, and other transactions originating from other networks also reach this network, this particular node, and likewise the blocks also. So that is how this fully decentralized peer-to-peer network works. So normally these normal nodes will be communicating with this node, and then it gets the peers, and it now has formed this set of nodes which are its peers, and then whatever transactions this node carries out, so those will then eventually be spread to the internet network, and from there also it will come back here. So whatever we are showing as the outgoing arrows, of course, this is just to denote that they are peers, but actual communication will be both ways. So as of now, we are showing all these as a normal nodes, like all its peers are really good, nice people. Now, what happens if then some attacker node or nodes, they try to uh, mm, see, the goal of this is, first let me tell you so that you can follow what is being explained. The eventual goal is that this victim node will be surrounded by nodes which are part of the group of the attacker. That means that eventually the target is to make all the peer nodes of these victim nodes to be such that they are under the control of the attacker node. So in the previous example, so this victim eventually had these peers, and they are generally good nodes. One or two might be rogue, but because it has got several others which are good nodes, so it can actually carry out the regular operations. But in this example, as we'll see, that instead of all these nodes that are surrounding this targeted victim node being good, or at least part of them are good, and so on, the end target of Eclipse attack is to ensure that all its peers are actually these rogue nodes, and they are in the control of the attacker. And because it is now cut off from the rest of the network, so it's sort of eclipsed from the rest of the network, and that's why it's called an eclipse attack. So how it works is that this attacker node, first we are giving an overview that the attacker node will try to first they identify a victim, and then they will try to ensure that victim node, as it is initially say communicating with the with some of the good nodes, but the attacker nodes form part of its peer network. And then what it will do is that, so far there are some attacker nodes, some good nodes, and so on. But slowly, what the attacker node, the attacker group or the attacker will try to ensure that now this list of peers for the victim network, of course, as you can understand, that somewhere it must be maintaining internally what is its list of peers. So it is to be ensured by the attacker that that list that is maintained by the victim node for its peer, that should be filled up with only addresses of nodes which are indeed a part of the group of the attacker. So these are say set of addresses which belong, quote unquote, belong to the attacker. And once that is done, then the entire communication with this victim node will be controlled by the attacker. So that is what it will try to do. So, but of course, initially it will not be like this. So initially the victim node is interacting with some of the good nodes, but slowly what will happen is that the attacker node will be filling in that list of peer node addresses of the victim node only by other addresses which are part of the group of attackers. Uh, so, if you see this example, that after it has been done, we'll see how it is done. But the initial slides are trying to explain how or what would be done. So these attacker nodes actually will be now flooding this list of addresses for the victim node, so that it will not be able to communicate with any other outside world. So you see that the normal nodes which are there in part of the complete network, these are now cut off. So the victim node is now only connected to those attacker nodes. Now what can happen is that these nodes that we are showing as attacker nodes, they may not be actually physical nodes. So these victim nodes list of peer addresses, if these are filled with some addresses that belong to attacker's node, and some are filled with some junk addresses which actually do not exist, then also what will happen is that victim will not be able to communicate with those ones. So that is what the goal is. Now with that, what would happen is that this attacker node has now eclipsed the victim node from the rest of the network, and as a result effectively that attacker controls the end hosts. Okay, so what it means is that it is blocking the path from this to the rest of the network, but it is not uh, affecting the key infrastructure between the victim and rest of the Bitcoin network, meaning that it is not actually blocking the entire, say, the internet infrastructure and all that. So it is blocking its communication with the rest of the uh, Bitcoin network. Now, what is the advantage of that? So the advantage is that if, for example, this particular victim node, say it was also going to be a pool as well, had say 30% hashing power, and say the attacker has 40% hashing power, and the rest of the network, suppose it has got the remaining 30% hashing power. Now, what would have happened was that, see that we talked about that 51% attack in which this mm, uh, attacker had to get that 51% computing power to launch certain types of attacks like double spending and other types of attacks. But here, by uh, wisely partitioning this network, what is happening is that this computational power of this 30% hashing power of the victim network, that is not actually going against the working of the attacker, which say has 40% power. And then because all the communication to the network between this victim and the rest of the chain, rest of the network, sorry, so is controlled by the attacker. So even with 40% hashing power, it can do what otherwise it would have required, would have been able to do only with 51% computing power. This is because the whatever uh, transactions and other block information that this victim node is getting or it is sending, these are all controlled by the attacker, and it can actually feed it with fake such block information and so on. So now it is having 40% hashing power as compared to 30% for the rest of the network. And then the attacks that only could have been done with 50%, 51% attack computing power can now be carried out by the attacker. So that is what it means. So the attacker outcompetes each partition miner. So you see that that would mean that if this victim node was mining some blocks and the rest of the network was mining some blocks, but of course the attacker will be able to mine the blocks faster as compared to these networks, and hence its chain will actually become the longest. Now the question is that it is an interesting attack, as we have just now tried to explain. But question is, how will it really happen? So how will attacker do all this? Now, see, for any node, for this is something to do with how the peer-to-peer network is set up. So in any node, including the victim nodes, there are peer tables which are used to for it to communicate. Now remember that these addresses that we're talking about, these are real IP addresses, because the packets. So if you remember, we said that it runs on TCP. So it will have to have finally the socket address with the IP address and the port number. So these are real IP addresses. So these are not like those whatever we talked about, public key addresses and hash of that. And just to connect it to that discussion, so this is the reason why there we are not using those these IP addresses for the payment, because in that case it can be linked to some physical nodes and one can actually figure out who is the intended recipient of those cryptocurrencies. So that is why we differentiate between those payment addresses and these communication addresses. Now, so the attacker will populate these victims' peer nodes with its IP addresses. So that is what the attacker's goal is. So the victim node restarts and loses current outgoing connections, and the victim establishes all its new outgoing connections to attacker's IP addresses. So just to remind you that typically for a full node there are 8 outgoing connections and I think up to 117 incoming connections that are allowed. So what this attacker node will do is that it will slowly try to first ensure that all those 8 outgoing addresses are replaced by addresses of the attacker. Now you see that even if we did not have attacks, so this peer-to-peer network formation and maintenance for blockchains, that must have been following some standard protocol, and that also must also guarantee against situations where maybe one of the peer nodes is down, or this victim, not the victim, any given node can restart, I mean it shut down, restart, and so on, and as it restarts it should again start filling in these addresses. And from time to time you see that this is going to be highly dynamic. The network can change, like today it has got one node has got these 8 the peers with which it has got outgoing connections, say A, B, C, D, F, G, H, and then this B is down, and then node number I is to be connected, and those things can always happen. And from time to time, they have to communicate and send messages, and if they find that they are not getting enough responses, so they make an assumption that that is down, and in that case, what it has to do is that these set of peer addresses that are maintained in the tables, these are to be updated from time to time. So, and there are certain such types of ways of pinging these nodes, like say something like ADDR and these types of actions, and so on. So those would typically be actually updating what we are talking about in terms of these peer tables. Just again to remind you that the paper that we refer to has got very nice details of how these different tables are maintained and how the attacker would attempt to update those with its own IP addresses. So this is what I was trying to say is that this node actually has got this for its maintaining the peer-to-peer network has got 2 tables of IP addresses. One is called so-called new table, the other is triad table. So this new table is the one the node has heard about, and as I said that this ADDR messages are sent, and tried table is where with which that this node has peered previous, and also stores a timestamp for each IP, and this stores IPs in buckets. Now what happens is that this when node is trying to communicate, node will pick up an IP address with some probability from the new table and with some probability from the tried table. So the goal of the attacker is to fill in all these tried table entries with its own IPs and fill in the new table entries with some junk IP addresses. So if that is done, what will happen is that even with some probability, if it is picked up from the new table, then it will not be able to send it because the junk addresses means these are not valid routable addresses. So eventually it will fall back on the tried table, and by that time the tried table will be filled up with the IP addresses of the attacker. What is done is that to find, as I said, that choose this one, new or not tired, it should be tried table, and then an IP address with newest timestamp, and attempt an outgoing connection to that IP. So if it picked up, if everything was working normal, always be with the same connections, and it will not know about the rest of the network. So it picks up at random either new or tried table, and then an IP from one of the buckets. So it selects a bucket within that table and an IP from that bucket, and tries to set up a connection with that. So as I said, that populates the tables with attacker IP, so that victim node only connects to the attacker IP. So actually, as I said, that these attacker IPs are usually populated in the triad table, and the new table is populated with some junk IP. And also, what is important is that you see that what can happen is that slowly these get built, and the attacker need not or may not be able to do it in one go. So what it will do is that it has to keep refreshing those IP addresses. IP addresses always will have newer timestamps as compared to the IPs of the honest nodes, because otherwise, if honest nodes also try to connect while the attacker is trying to get control, then more and more of these entries in the tried table will have honest IP addresses with newer timestamps, and those are likely to be picked up. So this attacker will not be able to take control. And from time to time, what happens is that the attacker waits for it to restart, and when it restarts, it will see that which all were the latest IP addresses, and so that is what when it will start communicating with the attacker. And of course, restarting the node is pretty natural. That from time to time these security updates are there or software updates are there, and it is seen that most of the nodes would restart once a week or so, and with that the attackers, when it restarts, it will now fill in all its IP addresses with the attacker's IP addresses. So so when of course the buckets get filled up with these IP addresses, so it will have to evict some of the current ones and add new ones. So the typical bucket eviction strategy is to randomly select some 4 IPs and delete the oldest ones and insert new ones. So as I said, that if the attacker keeps communicating with this one with the victim with its IP address, and then the honest nodes do not communicate so often, so those will slowly get evicted out, and it will be filled up with the attacker's IP addresses. So attackers IPs will always have the most recent. So this is how overall this one works. And um, what also it does is that it will replace one IP with another. So what it does is that this triad table, it is attacker also, remember, attackers has to use a lot of IP addresses. Of course, it has to get those IP addresses. Okay? And there are different ways that it can get a block of IP addresses from the ISP and get use with these ones one after the other, or if not, it will use a bot to generate different of such like if it does not have a contiguous block of IP addresses, it will try to get different IP addresses, and then through a bot it will be trying to do this, send the messages to the victim, and then try to replace its buckets with the IP addresses of the attacker. So that is what is done with this Eclipse attack. And as I said, that you see that once this Eclipse attack is successful, and first of all, this 51% this can be done, and similarly also it can carry out that selfish mining attack, because now it will be able to generate its blocks much faster. So all these things, double spending, all these things now would be possible once this has been achieved. So as we discussed, is that this is something not at the high level application level protocol of the blockchain network, but at the lower level network level protocol of the network, which is actually vulnerabilities in that are actually used. And in the paper, they also talk about certain ways of how to counter these attacks. So we are not going into that. We are only highlighting what the attack is all about, and the further details are also there in the paper. The next attack that we talk about, this is what is called front-running attack. Now, here again, we are going back to higher level, so not at the at the network level. Now, this front running is an interesting concept, and it is first of all, it has been there independent of blockchains and cryptocurrencies. It is there in financial transactions. So, it is something like this, that if, for example, say Alice knows that so Alice works in uh, uh, an exchange where and I'm not talking about uh, these cryptocurrency exchanges, even a regular exchange, where it finds that someone, say a company is going to buy, has placed order for buying, say lots of a large number of shares for a particular company. So for a particular share this is going to buy, and it knows that when these shares are purchased, then the prices are likely to go up, because if it's a very high value purchase, so there will be more demand and it will raise the price. So what this person can do is that, seeing that this company is going to buy a lot of shares, if it can, before that particular transaction hits the market, what this attacker will do is, or the person who is the malicious user can do, is that can itself carry out some of the purchase of shared transactions, for example, and then till I mean when the price is still low, and then when this bulk purchase takes place by the company, which might be buying thousands of shares, and the prices go up, so this person will now sell the shares, okay, and just make a profit, because it got this kind of front running, that before that transaction took place, it carried out its own transaction. And if it waited, then what would have happened is that after the transaction, if it tried to carry out its transaction, by that time the prices would have gone up. So this profit would have been less. And that's why it's called front running. It is running in front of that other transaction. So that is what is done. And this is actually illegal and all, and the guidelines are there to ensure that if such things like that occur, then the persons will be punished. So that is about the physical world. But you see that in the world of cryptocurrencies, like blockchain based cryptocurrencies, there is no such central control and all. So there is nothing like you can say that we will take legal action and all that. So that's why it makes it very, very attractive for the attackers to do some kind of front running. But then, as you can understand, or you might wonder that, say someone, so we see that the Alice is going to buy, say, 1,000 make a transaction of 1,000 such cryptocurrency, say in the Ethereum network, like 1,000, say ethers. I mean, it's quite high, but let us assume that. So attacker knows that if that is done, then the price of ether will go up. Okay. So by the time the attacker knows, and how does the attacker know? Attacker sees the transaction in the Ethereum network and in a block and sees that Alice has posted that transaction. What the attacker has to do is that attacker has to buy, say, sums, whether 1,000 or 100 or whatever, before Alice's transaction actually get executed. So what it will have to do is that it has to somehow carry out its own transaction before Alice's transaction gets included in a block. So that is what the attacker needs to do. But attacker has seen that transaction that Alice has carried because everybody can see the transaction. But how can attacker ensure that his transaction will get included before Alice's transaction? This can be done because, say, Alice was willing to pay some gas price for including her transaction in the block, Ethereum block, say 5GOI, and now attacker, what it does is that it spends higher gas price, it offers higher gas price, and so the miner, when the miner sees that the transaction of the attacker is offering 10 times the transaction fee, then, as we have discussed before, then it is more likely the attackers would be interested in including that transaction in the next block. So it might leave out the transaction of Alice, or while ordering the transactions to be included in the block, the miner might put attackers in this one before that of Alice. So if you see that, if and since there is not much direct control about how this will be done with respect to some timestamp based ordering or so on in a decentralized network, so it is possible that this transaction of the attacker will get in first and he gets the profit. And it might so happen that it might also cause Alice's transaction to fail if the prices are going up because of attacker's transaction, and then Alice might not be willing to pay that higher price and so on. So I mean, depending on the motive of the attacker, that he and its impact on the transaction of Alice, certain different situations can actually occur, as we'll see. But the point to understand from this is that there indeed are possible ways of ensuring that by getting to see a transaction, attacker can do something to get his transactions included before the transaction of Alice. So this again, this paper is actually listed in the last slide of this presentation. That of course is a very easy to read paper, and it actually divides this or categorizes the front running attacks into three types. One is so-called displacement, one is insertion, and the other is suppression. And they said that they got so they actually and this is something interesting type of work that people see the various transactions and try to, and there are these millions of transactions, and they try to figure out whether certain types of attacks were indeed carried out, and by studying those they try to then characterize those attacks and then maybe give a name to it, and then try to organize the study in such a way that they can actually show the different categorizations like we are seeing here in this slide. And that's how people get to know about these attacks, and typically they also offer countermeasures, and often before they make it public, they share it with the blockchain developers so that they can fix it and make a new release and so on. So that is how attacker. So the Alice's function call is not important to the attacker. So what the attacker wants is that attacker wants to run first, and then after that, if Alice's call, whatever happens to Alice's call, that is not important. But Alice's attacker's transaction going in first is important. A typical example could be, suppose there is some again taken from the paper, is that there is a website address which is up for sale and you can pay in cryptocurrency to get it. So the attacker sees that Alice is going to buy it, but attacker wants to buy it before Alice. He finds that this is a good this is a good website address to buy. So Alice will introduce a transaction and try to front run Alice so that attacker's transaction go in first, and attacker gets that particular address, and then Alice will lose out. So Alice's function call will actually fail because attacker has front run that call. So that is what is typically called displacement. It is displacing Alice's transaction lower down. And insertion means that attackers, what it does is that attacker changes the state on which the Alice's function call was supposed to get executed. So, for example, attacker sees that Alice is willing to buy, say, one Bitcoin for, say, 105 Litecoins. Okay. So attacker sees that, and currently, say, this Bitcoin is trading at one Bitcoin equal to, say, 100 Litecoins. So what it does is that the attacker knows that Alice is willing to pay 100 Litecoins for one Bitcoin, but current uh, uh, selling price is one Bitcoin for 100 Litecoins. So what attacker would do is that as soon as the attacker sees this transaction which says that Alice is willing to buy one Bitcoin for 105 Litecoins, attacker will now buy say one Bitcoin for 100 Litecoins and then sell it to Alice at 105 Litecoins. So what happens is that had Alice's transaction got executed when it is trading at 100 Litecoins per Bitcoin, then Alice would have actually paid for 100 with 100 Litecoins to get one Bitcoin, because assume that there was no fluctuation in between. So the maximum price Alice was willing to pay was 105. So if she got it at 100, she would have been happy. But then, so that was the state that is at 100, Alice's function should have executed if nothing had happened. Now the attacker is front running her, and then he is now including his transaction of uh, buying at 100, and now also that transaction of offering to sell it at, say, 105. So as a result, now Alice would end up paying 105, which if this attack was not carried out, would have paid 100, and the attacker in between, just without holding it for long, made 5 Litecoins out of that. So that is a kind of insertion. So, and suppression is that this is only about trying to delay Alice's function call, and the researchers said they did not find too many of these, but there is one example, and we'll talk about that a little later. And also that front running could be like two types that say asymmetric, like it is just one or two at a time, and they are different types of transaction. So for example, Alice is trying to cancel an offer. We'll see one example again. Say Alice has placed an offer, okay, that say Alice is saying that I would like to buy, as I said, that uh, one Bitcoin for, say, 105 Litecoins. Okay. And then Alice decided to cancel it. Okay, so she now entered the canceling transaction. But Bob, this time, assume that Bob has so many Litecoins. So, so many Bitcoins to sell to Alice. So as soon as the attacker sees that Alice is trying to cancel it, what the attacker would try to do is that whatever was the offer before this was cancelled, it will front run and put its own transaction that will actually fulfill that order of Alice. That means because it is available at 105, so Bob will now, or the attacker, if Bob is the attacker, will actually carry out fulfilling of that order transaction by in fact trading that 105 with Alice. So the point here is that Alice had already put her transaction of cancelling it, but seeing that Alice is cancelling, Bob will create his transaction of fulfilling that order and then front run it before that cancellation transaction of Alice. And all these are going to happen if this attacker can make sure that he can get his transaction executed before the one it is trying to front run. And bulk means that attacker is trying to run a large set of functions, and Alice is trying to buy a limited set of shares offered by a firm on a blockchain. So, this is like a lot of, as I gave the example, maybe someone is trying to buy a lot of shares, and the other one has a limited number. So what it wants is that it tries to carry out its own transaction. So both of these are like buying of things. These are similar types of, these are not asymmetric like cancelling and fulfilling. And then the attacker will try to front run his set of functions before uh, Alice's transaction in the block. Now, this is this example, as I said, that these markets and exchanges so spotting a profitable cancellation transaction. So here, as you can see, that Alice decided to cancel that order 100 that transaction, and then there is a buy for 101 and so on. So what happens is that this adversarial this attacker, what it will do is that it will add this buy order 100. So this whatever Alice was trying to cancel that order 100, now this attacker is fulfilling that order by offering to buy this 100. And after that, this cancel will not take place because this buy will front run it, and then now Alice's cancellation transaction will not succeed because that buy has already been done. So you see that uh, so the if the miner actually is part of the adversarial users, then it is up to the miner to decide. And of course, the ways by which the attacker can actually influence is either to bribe, quote unquote bribe, or willing to offer a higher gas price and so on to ensure that his transaction goes in first. So this is a typical example of a front-running attack. Now, this is one other example that is very interesting, and that is what we mentioned, that these researchers, they found only one example of this suppression attack, and this is the one that we are describing here. So, I mean, again, once again, it is talking about driving miners for prioritizing or something. So, or providing higher gas price. So, this was this Homo 3D game. So this was very interesting, and this actually is in line with what I said, how researchers actually study all these transactions and related data on the blockchains, and by by carefully scrutinizing those, they come up with situations where indeed maybe something which was dishonest had been carried out. Now, this is an interesting example, so that's why I thought of explaining it to you a little bit. There was this Homo 3D game. What it says is that it has got a timer, okay, that it is going to end, say at some point of time, say at 1 p.m. on say 28th of October 2021. But every time, okay, and the last person to buy a ticket, so one has to buy a ticket for this, paying some price on a particular blockchain. So suppose one has to pay Ether to buy a ticket. Okay, and the person who who purchases the ticket last is the one who will get the jackpot. Okay, so will win the game. So and every time someone uh, buys a ticket, the timer is extended by 30 seconds. So if it is at 1 p.m. On 28th October 2021, and say I buy a ticket now, it will be extended by 30 seconds. So it is at 1 p.m. 30 seconds that now it will. So now again someone buys, then it will again be extended by 30 seconds and so on. So you see that people would be buying it. If nobody buys, nobody wins. So people will be buying it, hoping to be the last person to buy the ticket. But then, as he buys, it will get extended by a little bit. And then, just very close to that, say, if nobody had purchased, say, someone had purchased last at 10 a.m., and very close to 1 p.m., somebody will purchase, expecting that he will be the last person. So just maybe a few minutes before 1 p.m., somebody buys. But as soon as he buys, it will get extended by 30 seconds. Now, if somebody says, "Oh, there is some more time left, and let me buy it," and again it will get extended by 30 seconds and so on. So, what people had expected that this will never end, okay, because people will be buying the tickets, and in the process, they are actually paying that ether price to the organizer of the game, and who now actually increasing also the jackpot value. Then what happened? It actually really got concluded, and the person who, I mean, whoever, not the person, the particular account, the user who owned got a lot of money. Okay, so then people felt that it was not likely to complete, but how did it conclude? And then this got paid. So what this guy did was that just 3 minutes before that current conclusion time, say at before 1 p.m. So just at maybe 12:57, what he did was he actually purchased a ticket and then immediately also sent multiple very high gas price transactions through her own DF. So the attacker had a lot of such DFs already launched. And then in order to choke the Ethereum network, what the attacker did was that attacker carried out these multiple such very high gas price transactions through her DF. So all the different miners, they were now mining all these transactions which were launched by the DApps instead of mining any transaction, maybe a subsequent user who possibly would have liked to buy another ticket. So what it effectively did was it completely front run the other transactions who were of users who were trying to buy, and then this time out of 1 p.m. was reached, and then this guy got back got all the whatever money out of the game. So this is very interesting and practical example of how front running indeed works. So these are the different types of attacks we thought of discussing, and as we said that it congested the network, and this got completed like this. So these were the different types of attacks we wanted to discuss, and then the final topic here is this notion of tesseract, which, if you remember, that when we talked about interoperability, we put it on hold for some time. So now we will talk about it, so that because you know the different types of attacks, you can better appreciate how these are handled in Tesseract. So it is a secure real-time cryptocurrency exchange, which was, this work was published in ASEAN conference on communications security in 2019. Uh, so what it does is that it, of course, first highlights that centralized exchange designs are vulnerable to theft of funds, which already we have seen. But the decentralized exchanges, they cannot offer real-time cross-chain trades because they have to wait for the transactions to actually uh, be included in blocks, to be confirmed in blocks. Then only those transactions can be held as valid. But centralized exchange, what they do is that they do not do like this. They actually maintain your like share market, the exchanges. So they are these brokerage firms, they will hold your money, and then as you trade, it will do those transfers, and after some time you can get a payout and all. Centralized exchanges actually hold on to your money and then do the trading, and then that will get reflected in the blockchain from time to time. But of course, we have seen that it could be vulnerable to theft of funds. So what Tesseract does is that it tries to have a balance between these two, that it's a real time, it is as fast as centralized exchanges, and that means that this buy and sell, these prices are available in real time, and the parties can modify their trading positions in milliseconds, which is done in normal exchanges also. So in centralized exchanges, and then what it does is that it lets people see the offers, and then they can change their own offers and so on. And it also supports cross chain asset exchanges, like from one particular currency to another. These types of exchanges also is supported by this Tesseract. Now, so it is also secure against theft by exchange operators. So as I said, that it tries to address the vulnerabilities of centralized exchanges, and at the same time
it offers this real-time trading abilities to its users. So what we'll do is that it will take maybe a bit of time. So instead of going into its details, I will stop here. And in our next class, we will wrap up this discussion because there are about 5 or 6 slides, and I will need maybe about 15 minutes or so. So what we'll do is that we'll stop here, and next week we have, I think, Thursday is a holiday due to Diwali, and Wednesday we have a class. So Wednesday I will first wrap it up, and then we'll move on to our discussions on different applications of blockchain. Uh, so let me stop here. Is there any question? Professor Chakraborty, is it fine that we do like that?
Yes, absolutely fine.
Okay, I will wrap it up, and then we'll start our discussion on the applications next
Oh,
week. And also tomorrow we have initially again a 10-minute quiz like last week we did. Uh, Please join as early as possible so that we can then move on to our tutorial and discussions on the hyperledger. So I'm stopping the recording now.